Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Boundary conditions. The property of a conductor and the boundary conditions which prevail in respect of conductor free space interface. The two most important characteristics of a conductor in relation to electrostatics are: 1. The charge density D in the interior of a conductor is equals to 0. And second condition is field intensity inside the conductor is 0. Let us assume that the charge distribution inside a conductor is distributed with the results that a large number of electrons appear in the interior of the conductor. These electrons carry negative charges. As such, they set up electric field inside. Influenced by these fields, the electrons tend to move and they accelerate, being repelled by one another. Eventually, they reach the conductor surface. Since the conductor is surrounded by an insulating medium like air, the negative charges of the electrons get deposited on the surface of the conductor, thus establishing surface charge density. Inside the conductor, the total positive charge and the total negative charge balances. With the result, there is no volume charge density inside the conductor. Hence, the charge density of the conductor is 0 even there is a surface charge density. The field intensity inside the conductor is 0 is a direct consequence of Ohm's law. If there is an electric field, there would be current, and this would invalidate our assumption of static electric field. Hence, field intensity must be necessarily be 0. So conductor free space interference, this is conductor and this is free space. So I'm drawing a tangent here. This is 90 degrees. This is normal and this is tangent. D tangent, and this is my D normal. D is equals to epsilon naught E T E M D E A B C and D. And this, let it be delta H. This length is del W. Now the field intensity E is divided into two components, that is ET and EM. Similarly, charge density D is divided into two components, that is DT and DN. So tangential component ET equals to 0. When ET is 0, DT also becomes 0. Now consider a closed surface area AB, CD, A. Let AB and CD equals to del W, BC, AD equals to del H. We know closed loop of E dot dl equals to 0. Integral A to B plus integral B to C plus integral C to D plus integral D to A equals to 0. AB along ET multiplied by del W integral B to C E n half delta H plus 0 plus E n half delta H equals to 0. When delta H tends to 0, these two terms En plus En will be equal then gets cancelled, then you are going to get 0. The only term remaining is Et delta W equals to 0, and delta W is a finite, so it cannot be equals to 0. Then Et equals to 0. So insulating medium, it's a conductor and free space. Here I am considering a cylindrical surface. This is delta S. The height of the cylinder is delta H. Q equals to closed surface d dot ds. Q equals to integral top plus integral bottom plus cylindrical surface is equals to 0. So bottom surface is equals to 0 since this is inside the conductor. Cylindrical surface is equals to 0. Only the top will remain, that equals to dn is normal, dn dot delta S equals to Q. Q is equals to surface charge density multiplied by the area. dn dot delta S equals to rho S dot delta S. From this two we can write dn equals to rho S. This implies that the flux leaving the surface normally in magnitude is equal to the surface charge density. The summary is, inside the conductor, the static electric field intensity E is equals to 0. And the static electric field intensity at the surface of the conductor is directed outwards normal at the point on the surface equals to En. Tangential component of the electric field intensity, that is Et, equals to 0 at the conductor surface. In other words, the conductor surface is equipotential surface. The potential field given by the equation V equal to 200 x square minus y square at point P 3, minus 2 and 4 on conductor free space boundary. Find V, E, En, Et and rho S at point P. Now from this we can write, since it is in conductor free space boundary, Et equals to 0. V equals to 200 x square minus y square. Substitute the value of x and y from the point P. Then you are going to get 200 3 square minus of minus 2 whole square, which is nothing but 9, and this is 4, 5. So 200 into 5,000 volts. E is given by minus gradient of V, that is equals to minus dou V by dou x Ex plus dou V by dou y Uy plus dou V by dou z Uz, dou by dou x of 200 x square Ux plus dou by dou y of minus 200 y square. Exact term is 0. Then minus 400 x minus 400 y. This is along Ux and this is along Uy. Substitute the value of x in this. Then minus 400 x is 3. So 3 times, this is 1200 x minus 400 into y is minus 2. That is minus of minus 800 Uy. E equals to En. So En equals to 1442.221 volts per meter. Rho S equals to dn, which is epsilon naught En, epsilon naught E. Then in vector form, epsilon naught is 8.854 into 10 power minus 12 of minus 1200 ux minus 800 uy minus 10.625 ux minus 7.083 uy square root of 10.625 whole square plus 7.083 whole square, which equals to 12.77 nanocoulombs per meter square. This is also nanocoulombs per meter square.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share, and subscribe. Thank you for watching the video. Please stay tuned for more videos.